Welcome back to the analog electronic circuits course, and today is lecture number 11, and the plan for today is that we are going to continue where we had left off on the problem of swing limits, and we are also going to look at a few multi transistor amplifier circuits. Okay. So, in the last class we were looking at this particular amplifier structure. So, we had chosen 10K over here, 10K over here, 1K over here, right, and as far as I remember this was 5 volts. This current we had chosen was 0.1 milliamperes, and the voltage over here was 4, the voltage over here was 0.1, and the voltage at the gate was 0.8. So, this was my setup in the last class, and we are always going to so this particular amplifier had a gain of approximately 5, it is actually less than 5, but let us assume that the gain is 5. Minus 5. If I increase the input by 1 millivolt, then the output is going to decrease over here, it is going to decrease by 5 millivolts, right. So, you will see minus 5 millivolts at V out. Okay, so, this was what we had done. We had chosen some values of k and etc., but those do not matter to us right now. All right. Now, when you are evaluating the swing limits, there are two things that you have to be reminded of. Item number 1 is that VDS has to be greater than VGS minus VT at all times. This is item number 1, and item number 2 is that ID has to be greater than 0 at all times. These are the absolute currents and voltages, right. Absolute means the sum of the DC operating point and the small signal and the incremental signal. Now, this just by the way, the incremental signal need not be small all the time, right. For small signal analysis to be valid, it has to be small, but otherwise it does not really have to be small, it is just an incremental signal, and the incremental portion always goes through the is a short circuit through the capacitor, right. So, whatever it is, small, large, it really does not matter. Okay. So, from item number 1, what did we get? We said that VDS has to be greater than VGS minus VT. Of this, both the source as well as the drain are moving, right. This source is not really static. If there is a signal current on ID, then the source voltage will also change. However, if you look at equation 1 carefully, you will see that the source voltage will cancel out from both sides, which effectively means that VD has to be more than VG minus VT. Okay. And the gate voltage is the DC gate voltage 0.8 plus V in. VT is 0.5, that is what we had picked in the last class. And what is the drain voltage? Drain voltage is 4 plus the extra drain voltage, incremental drain voltage is V out. But V out is minus 5 times V in. Okay. So, instead of writing V in over here, let us write minus V out by 5 and then put the V outs together, put the constants together. Okay. And what do you end up with? So, you end up with 1.2 V out has to be greater than 3.7 minus 3.7. Okay, or in other words, V out has a lower limit of minus 3.1 or so, whatever it is, right, 3.7 by 1.2. Fine, is this okay? So, this is what we had done in the earlier class. This was evaluating the first condition. Okay. Now, right now I am doing it very mathematically, but these are limits that you can actually observe on the circuit itself. You do not really have to do it mathematically all the time, right. This mathematics is not really that important. All right. The second one is ID has to be more than 0. So, how do we evaluate that? ID is nothing but capital ID, which is 0.1 milliampere, plus small ID. Okay. So, that means, this basically means that small ID has to be more than minus 0.1 milliampere, all right, which basically means that the signal current, only the signal current going up, maximum signal current going up is 0.1 milliampere. Okay. Now, where is this 0.1 milliampere go? Where is this going to go? It is going to go up through the source and then split, in this case 2 equal portions, all right, 0.05 milliampere and 0.05 milliampere, right. It is going to split up into these 2 equal portions, and 0.05 milliampere is going to drop across 10K over here, for example. And how much voltage will it create at V out? .05 times 10K is 0.05 milliamperes times 10K is 0.5 volt. So, the maximum amplitude on V out is 0.5 volt, because the maximum current that it can draw, this load can draw out of the drain is 0.05 milliampere, and when that 0.05 milliampere comes through, 0.05 times 10K, you get half a volt of amplitude. Is this okay? So, if V in was to be a sine wave, suppose V in was to be a sine wave, then what would be the maximum amplitude that you would have at V out? V in is a sine wave, so V out is also a sine wave inverted. Okay. So, gain times, all right, the amplitude of V out is the gain times the amplitude of V in, all right. It is a sine wave, purely symmetric. Now, V out is allowed to go down to minus 3.1 volt. On the other hand, V out is allowed to rise by a maximum of 0.5 volts. So, the maximum it can dip is minus 3.1, maximum it can rise is 0.5. What does this mean? What is the symmetric maximum amplitude of V out? It is only 0.5. So, symmetric amplitude at V out. So, V out can go up and down by 0.5 volts. So, the largest sine wave that you can see at V out is 0.5 volts. You will not see a larger sine wave than that. Is this okay? All right. So, this kind of summarizes. So, we did 2 examples, one actually more than 2, 3 examples we did. One without the source, 2 of them without the source degeneration, one with the source degeneration, and we saw in different ways what happens, what are the maximum swing limits at the output node. All right. There are all kinds of other topologies. You could, for example, have a common drain circuit, common gate circuit, all of those. They will also have similar computations with swing limits. You will have to go through those computations, right. There could also be questions where you say that you declare in advance that I want a maximum symmetric amplitude of 0.5 volts. What are the resistor values? Okay. Or you could say that we need to equalize. Another problem would be that let us try to equalize these 2 limits. There is no reason for V out to have a larger dip than a crest, right. The size of the crest and the size of the trough, these should be equal. So, let us try to equalize the maximum amplitude on the positive as well as negative side, okay. And therefore, what are the resistors going to be, right. So, there are a variety of problems that you can have with these swing limit calculations. Okay. You will get some practice with these problems in the assignments. Yeah. Next, what we are going to do is we are going to move on to the next topic. We are going to try to make amplifiers or structures, circuit structures, which have more than one transistor. So, first let us try to understand if there is any problem with the common source amplifier. Is there any problem? This common source amplifier is great. Is there any problem? Okay. So, this is the structure of the common source amplifier. Can we list out the different problems of this circuit? Okay. So, problem number 1 is that the gain, is it a problem? The gain is negative? No, that is not a problem. The gain of this structure is minus GM times. So, remember in the small signal picture, okay. How do you find the quickly look, think about the gain of this structure? Very quickly, you do the Norton equivalent, right? Try to do it in your mind. This is a short circuit, all right. So, experiment 1 for Norton equivalent is to do the short circuit test. I do a short circuit over here. So, RD does not matter, RS never mattered anyway, RD does not matter, R1 and R2 never really matter, right. So, I apply a signal at the input. What is the current in the short circuit? Inside the MOSFET there is RDS and there is GM, okay, that is inside the MOSFET. So, I apply a signal at the input. GM produces a current GM times V in that goes into the output short circuit. What about RDS? RDS, the output short circuit has grounded on one side and the source has grounded on the other side. Okay, so there is no current in the RDS, and that automatically means that the short circuit current is GM times V in. All right. So, the transconductance is nothing but GM, that is the transconductance. So, you see very quickly you can do these things, you just have to help yourself by not revealing, not drawing the small signal, full small signal picture every time. See, this is after all engineering, and in engineering we like to skip a few steps. So, try to skip some steps. All right. So, short circuit current is GM times V in, and there too I am not really writing V in, I am writing the short circuit transconductance, that is GM, that is just GM. Okay, because later on I am going to. So, what will you do? Short circuit current is GM times V in, the output impedance is going to be something, right. So, V out is going to be GM times V in times the output impedance. Then after that you are going to do V out by V in is equal to GM times the output impedance. Okay, so that is the strategy with some sign. The sign is negative in this case because the current is coming this way in the short circuit current. Okay, never mind, just focus on the idea. The idea is that when we talk about the Norton equivalent, there are many steps. You do the short circuit current, but then do not write the V in at all, you just write it as a transconductance GM, right, and then multiply it with the output impedance, and that gives you the voltage gain. All right. So, this is the strategy that we are going to follow. So, transconductance in my case is just minus GM, and then the output impedance. What is the output impedance of this circuit? So, if I look in from outside, this is a short circuit, I look up, I see RD, I look down, I see, yes, you have got a GM and you have got RDS, but the input is grounded. When you are doing the output impedance, the input has been nulled, right. Nulled means that voltage source has been made equal to 0. Okay, so, input is grounded. Input is grounded means that gate voltage is grounded. If the gate voltage is grounded, source is grounded. So, GM does not matter at all. So, all you have is RDS, right. So, looking down I see RDS, looking up I see RD, which means that the output impedance is nothing but RD in parallel with RDS, and that is it. Okay. So, this is how we do the analysis. You find out the short circuit current, or rather the short circuit transconductance, find out the output impedance, multiply them, you are going to get the voltage gain. Okay. So, this particular amplifier, this common source amplifier has an output impedance RD parallel RDS, has a transconductance of GM, and therefore, the voltage gain is GM times RD parallel RDS. All right. Now, RDS is limited by the value of GM. Did you know that? No. Okay. So, when we do the MOSFET, when you look at the MOSFET characteristics, you think of it as two straight lines. This is one straight line and then you think of it as another straight line. Okay. For the ideal MOSFET, this second straight line is going to be parallel to the x axis, but no MOSFET is going to be ideal. All right. So, this is what we have. All right. So, this is the MOS characteristics that I have redrawn. Now, ordinarily in this region, in the flat region of the MOSFET, ID, you would say that ID is some constant k times VGS minus VT the whole square. Okay, this is what you would say ordinarily. However, that is not really the case, there is some slope to it. All right. So, what we try to do is we try to model this as a straight line. First of all, we try to model this as a straight line and then we say that ID is k times VGS minus VT the whole squared times 1 plus some lambda VDS. Okay, so, this is a constant times a function of VDS, constant with respect to VGS, right. Once I fix VGS, this entire portion becomes a constant. When I fix VGS, this entire portion becomes a constant. This still remains because VDS changes and it starts looking like a straight line that cuts the x axis VDS equal to 0 at the original current. Okay. So, the original current times 1 plus lambda VDS, the original current times 1 plus lambda VDS. So, this is the model that we have, and hopefully all of these have a similar slope, okay, or rather a slope that is proportional to the current. Fine. So, when you do partial derivative of ID with respect to VDS, what do you get? When you do partial derivative of ID with respect to VGS, so there are two partial derivatives, right. ID is now a function of VGS as well as VDS. You can do dou ID by dou VGS, you can do a dou ID by dou VDS. If you do this, what do you obtain? You obtain 2 times k times VGS minus VT times the rest of the stuff. Okay. And over here, if you suggest that lambda happens to be a small number, lambda should be a small number, right. Lambda is related to the slope of this graph of this flat portion, right. So, that should be generally a small number. So, if lambda is a small number, then this is nothing but 2 k times VGS minus VT, right, and that is, you know, two ID by VGS minus VT Okay. You could also say that that is equal to VGS minus VT is square root of ID by K. Okay. So, multiple possibilities you can look at. Okay. So, in this case you have eliminated K altogether, in this case you have eliminated VGS altogether, in this case you have eliminated ID altogether, right. So, you can have so this is GM. Okay. So, GM could be thought of as a function of K and VGS, this capital VGS. GM could be thought of as a function of ID and VGS and not K, and GM could be thought of as a function of K and ID and not of VGS. So, you can manipulate as you please. Fine. All that you are making a few assumptions here. You are making an assumption that lambda is small, and that is a very convenient assumption, because otherwise this factor is going to linger on and it is going to create a lot of difficulties all over the place. Oh, this is accurate, is it? You do not really have to, okay, fine. This expression is correct no matter what. All right. So, this is GM, this is what happened when you did a derivative, partial derivative with respect to VGS. Now, you could also do a partial derivative with respect to VDS, and what happens in that case? In that case what you get is K times VGS minus VT remains, and then you get just lambda. All right. And K times VGS minus VT the whole squared is approximately equal to ID and you have got lambda, which basically means that the slope of this curve is lambda times ID approximately. Is this okay? This also means that RDS, this was GDS. RDS is 1 by lambda ID. What are the units of lambda? What is the unit of lambda? Look at this expression, 1 plus lambda VDS. What is the unit of lambda? There is a 1 over here and there is a lambda VDS. You are adding two things. On one hand you are adding a 1, on the other hand you are adding lambda VDS. So, what is the dimension of lambda? 1 by volt. Okay, it is 1 by volt, because only then lambda VDS becomes a number. So, the dimension of lambda is 1 by volt. 1 by volt means volt is in the numerator divided by current, that is resistance. So, it all checks out, okay, all satisfied. All right. So, RDS is going to be typically 1 by lambda ID, where lambda is going to be given to you, right. So, depending on the value of ID you get RDS. Typical values of lambda would be 0.1, 0.01, 0.05, something like that. Okay. But what is important is that RDS is inversely proportional to ID typically, all right, and I need you to see that RDS is inversely proportional to ID. So, if I jack up ID, RDS is going to drop. On the other hand, given a device, right. So, if I have given you the device, K is fixed, you can't do much with K, all right. And given a bias current, if I give you the bias current, then ID is fixed. So, GM is 2 times square root of K ID. You have eliminated VGS altogether. You take whatever VGS you require for that particular ID and that particular MOSFET. All right. So, GM is proportional to square root of ID, RDS is proportional to 1 by ID, all right. The best possible gain coming out of this amplifier, best possible, is when RD is very, very large, is GM times RDS, which means GM times RDS, which means that if I decrease ID, look, let us do this. GM is equal to 2 times square root of K ID. RDS is 1 by lambda ID. Okay. The gain of the circuit, best possible gain, intrinsic gain of the MOSFET is GM times RDS, right. By the way, both of these are slight approximations, but that is okay. So, this is equal to 2 times root K times divided by lambda divided by root ID. Okay. So, what this means is that if I decrease ID, then hopefully the intrinsic gain of the MOSFET is going to increase. So, if I decrease the value of ID, then hopefully intrinsic gain of the MOSFET is going to increase. This is general suggestion. Okay. However, you can't do that much. You have to maintain the MOSFET in strong inversion for all these equations to be valid. Okay. These equations are valid only when the MOSFET is in strong inversion, not otherwise. Okay. All of this modeling, all these models, right. So, if I keep decreasing ID, then suddenly the MOSFET is going to drop out of strong inversion. What is strong inversion? What is strong inversion? Oh, okay. You don't know. So, the MOSFET has 3 regions of operation. Here the MOSFET has 2 regions of operation. Region 1 is the linear region, where it goes like a straight line through the origin. Okay. That's called the linear region, and the other region is the flat region. So, this is called the saturation. All right, and these are 2 regions of operation of the MOSFET based on the value of VDS. So, here the function is, it is a function of VDS. If I change VDS, you can go from linear to saturation and vice versa. Fine. The MOSFET has 3 more regions of operation, which are independent of those 2. And in the earlier case, you were changing VDS and going from one region to the other. Here, you are going to change VGS and go from one region to the other. All right. And mostly this entire region is called strong inversion. This entire region is called weak inversion, and this region is called moderate inversion. All right. And what is this number over here on the x axis? So, this place is Vt. Remember, the current is a function of Vgs minus Vt. You say K times Vgs minus Vt the whole squared, for example, right. So, K times Vgs minus Vt the whole squared is valid in strong inversion, right. When Vt equal to when Vgs is equal to Vt, the current is not really equal to 0, it is something small. So, this k times Vgs minus Vt the whole squared So, this equation, look at the 3 regions. Vgs is much more than Vt, this is valid. Vgs is equal to Vt, right, you get your answer as 0. But when Vgs is equal to Vt, if you take a MOSFET to the lab and apply the right Vgs such that it is equal to Vt, you will find that there is still some current. Okay. So, this equation is no longer valid. This region is called moderate inversion, and when Vgs is much less than Vt, right, that is this region, right. Over here it looks like the current is equal to 0, right, but if you actually measure it in the lab, it is not really equal to 0, all right, it is still going to be something. So, that region is called weak inversion. So, we have 3 regions of operation: strong inversion, weak inversion, moderate inversion. Strong inversion, moderate inversion, weak inversion. Now, the standard definitions for these regions are: you are in strong if Vgs is greater than Vt plus 0.2, okay, and you are in weak if Vgs is less than Vt minus 0.2. Okay, these are the standard definitions. And you are in moderate if Vgs is in between the two. Okay, so, the limits are you have Vt minus 0.2, you have Vt plus 0.2. If Vgs is more than Vt plus 0.2, then it is called strong inversion. If Vgs is less than Vt minus 0.2, it is called weak inversion. In between, it is called moderate inversion. And the standard understanding is that this particular equation that I have, Id equal to k times Vgs minus Vt the whole squared, this equation is valid in strong inversion, which means that Vgs has to be more than 0.2. Okay, only in such a scenario this particular equation is valid. Now, what is the equation in moderate, what is the equation in weak? I am not going to reveal these to you right now, because these are all matters of I mean number of people are doing PhD theses on these topics, how to model the MOSFET, what are these equations, so on and so forth, and it's not a matter of teaching in a class, right. This is not a matter of classroom teaching. This is not anyway the objective of the course, right. The objective of the course is to take the MOSFET and use it, not to delve into the physics of the MOSFET and so on, right. So, we need to understand that what is the takeaway. The takeaway is that there is a lower limit as to how low Vgs minus Vt can be. Vgs minus Vt should be more than 0.2 to be in strong inversion. All right, if Vgs minus Vt is not even 0.2 volts, then maybe you are not in strong inversion, maybe this equation is no longer valid. All right, is this understanding okay so far? All right. So, let us get back. So, what I am observing over here is that my intrinsic gain goes up when Id goes down, all right, but there is a limit to how low Id can be, right. What is Id now? Id is k times Vgs minus Vt the whole squared in strong inversion. So, root Id is root k times Vgs minus Vt in strong inversion, right? You plug this in over there, root ID, what do you get? Root k cancel out. So, you get this entire expression Gm RDS is equal to 2 times lambda VGS minus VT. So, there is a limit to VGS minus VT. The lowest VGS minus VT that you can have is 0.2. Okay, you can't have a VGS minus VT that is lower than 0.2. So, if this is, if you want to remain in strong inversion, if all of this analysis is correct, right. So, that is one limit that I have. Now, if VGS minus VT is 0.2, then this entire thing is 10 by lambda. Is this okay so far? Okay. So, Gm times RDS is limited to 10 by lambda. Now, what is lambda? Lambda is the slope of, lambda ID is the slope of this curve, right. Whatever the current, bias current is, I do not know, lambda times ID is the slope of these curves, these set of family of curves. All right. Typical values of lambda is 0.1, 0.01, 0.01 is too low for lambda, 0.1, 0.05, these are typical values of lambda, which automatically means that 10 by lambda is going to have a limit, right, how large it is going to be. You will have something like 100 as the intrinsic gain of this particular MOSFET. So far so good? Okay. So, let us get back. My question to you was, what are the drawbacks of this circuit? So, the number one drawback that I have is that this circuit has limited gain. All right, gain of the circuit is limited. First of all, the intrinsic gain is Gm times RDS. The output impedance is not RDS, it is much smaller than RDS, it is RD parallel RDS. Okay, that is number one. Okay, then you are saying that Gm times RDS has an upper limit, has a ceiling. Okay. Now, how much lower is RD compared to RDS? Is there an upper limit to RD? Can RD be infinite? Can I have RD to be infinite over here? No. Why not? Why can't RD be infinite? If RD is infinite, then where is the bias current? You are not going to have any bias current. Okay. So, suppose you have got bias current ID, all right. Suppose you need a certain VDS, how much VDS do you need? More than VGS minus VT by the swing that you want. Okay. So, let us say you have kept your VGS minus VT to be at its lower limit, that is 0.2 volts. Okay. So, VGS is 0.2 plus VT, all right. Because you want the best possible gain. So, you keep VGS at the lower limit 0.2 plus VT. Okay. That means that the lowest value of VDS has to be more than VGS minus VT. VDS certainly has to be more than 0.2, certainly. Okay. Now, this is the operating point VDS. The actual VDS has to be even more than even actual VDS, small v sub ds, which is equal to operating point VDS plus small VDS, even this has to be now more than 0.2, right, because at all times you need VDS to be more than VGS minus VT. Let us assume that the gain of the amplifier is so large that the gate is not really moving around, right, the drain is moving, but the gain of the amplifier is large enough that even when the drain moves, the gate, because the gain is large, the gate is not really moving very significantly. So, forget any signal on VGS, as in VGS is not really changing, this is more or less constant. Okay. So, I have therefore, at all times I need to satisfy capital VDS plus small VDS has to be more than 0.2. Okay. Now, small VDS is changing with time, it goes up, it goes down, right, it goes positive as well as negative. Okay. Suppose I want a good amplitude out of this MOSFET, right, some reasonable amplitude at the output. Let us say you want if your power supply is VDD over here, I do not know what the power supply is, maybe it is 5 volts, maybe not. Suppose your power supply is VDD, I would like to have at least half of the power supply as a quarter of the power supply as the amplitude of VDS, symmetric. So, VDS is going up and down by a quarter of the supply voltage, okay, or in other words small VDS is equal to VDD by 4. So, the lowest it is going to go is minus VDD by 4, which now means that capital VDS has to be more than 0.2 plus, so this level. So, this is my, even this has to satisfy greater than 0.2. So, let us say this is equal to 0.2, right. In that case capital VDS is 0.2 plus a quarter of the power supply. Fine. So, automatically this is going to reveal what is the value of RD. I am telling you that capital VDS is 0.2 plus a quarter of the power supply, all right. Let us say this source voltage is 0, all right. Let us say this RS is 0 ohms, let us make life easier, right. Let us not complicate ourselves, let us say RS is 0 ohms, right. So, this node is at 0 volts. Suppose this node is at 0 volts, where is this node at? This node is at VDD minus RD times ID, ID times RD. And what is VDS? S is at 0, VDS is also equal to VDD minus RD. Okay. And now you say that you want VDS to be 0.2 plus VDD by 4. All right. So, automatically you are saying that IDRD take IDRD to the other side, that is equal to 0.75 VDD minus 0.2. Okay. So, ID times RD has a value automatically. All right. Now, you can say let's look, how does this change with the swing? So, if I decrease the allowable swing, then this increases. So, ID times RD increases. Okay. So, if I have declared the value of ID, for example, RD is automatically declared. If I make RD very, very large, then ID is going to be very, very small. Okay. But ID has a lower limit, does not it? ID has a lower limit, we just saw in the earlier one, right. To remain in strong inversion, ID, I mean VGS minus VT has a lower limit, right. So, ID has a lower limit, k times 0.2 squared is the lower limit for ID. So, this ID over here is nothing but k times 0.2 squared. Right. What I am trying to drive at is that there is a limit to how large RD can be. RD can't be infinite. Okay. If you want to make RD too big, then first what is going to happen is the swing is going to drop. Okay. For example, if RD is huge, what is going to happen? If RD is huge, automatically you need this number to increase. There is a limit to how large this number can be. Can it be can it be more than 1? No, it can't be more than 1, because you got this as VDD minus VDD by 4. You said that I want VDD by 4 to be the amplitude over there, okay, at least. So, there is a limit to how large this can be. If you want 0 amplitude over there, then this is just VDD. Okay. So, you can't have RD to be arbitrarily large. At best, even when the swing is nothing, right, there is no swing that you are going to allow, this is VDD minus 0.2, right. You have a lower limit to how low ID can be, accordingly you will have the value of RD. Is this okay? So, what do I have? VDD minus 0.2 by k times 0.2 squared. That is going to be the largest possible value of RD. What I am trying to hint at over here is that this RD is no good, right. There is a limit to how large this RD is. If I make RD to be very large, then the swing is going to go down. If I make RD to be very small, the gain is going to go down. So, this RD is playing spoil sport over here, this particular resistor. If I increase its value, swing is going down, and even then I can only increase it so much, there is a limit, right, even when there is 0 swing. If I decrease its value, the gain is dropping like a stone. Okay. The gain is already limited, it's going down even further. Okay. So, what we are going to do is, we are going to take this understanding and then we are going to try to solve the problem. This problem over here is RD. The gain is being limited by RD, the swing is being limited by RD. Now, let us try to solve the problem. Can we make better designs? Okay. Thank you so much.